Sometimes a process actually has two or more sub-processes that each by themselves have a pretty small spread, but when you check the total results, you will see a huge spread, and you might imagine that you have a very poor CPK, lots of outliers, but you may be fooling yourself because normality doesn't really apply to this. Hello, I'm Tom. Welcome to my channel where we talk about continuous improvement in an industrial setting. And today I want to share it with you. Well, actually it is one of the problems I have at the moment with one of the lines in my factory where we have a double dosing. Now, many actually of the lines in the factory where I now work have a double dosing. In the previous factory where I worked, we also had 4 or 6 or even 7 dosings at one time for the same product. So that means that even if one of your dosage systems has a very nice narrow spread, so it really creates a small band, right? The same product every time, but you have a structural difference between your two dosing sites, then the total spread that you see in your product will of course be more. You always have a bit of spread. That's what we talk about quite a lot on this channel. That is the whole premise of Six Sigma. You have a normal distribution because you have all kinds of variations in your process, and if you combine a number of separate variations, you almost always end up with a normal distribution. Now, that means that for our dosing system, we basically know that the underlying physical process has 2 normal distributions. What do we now get when we measure all of the packages coming out there? That is going to be a combined system. So we see values popping up from everywhere, but one of the important things is that we get quite a lot of values in both of these peaks, so to say. So this whole area is quite a lot of total values and not too many values to the sides. If you pick this and then just calculate a standard distribution, a standard deviation, and then plot again your normal curve, it will do something strange because it will make a relatively wide spread. You would expect, of course, here to be the peak, right? So this is what we would expect. But then instead of dropping very steeply, what it does is it stretches out your sides. This is not completely correct. Draw it in Excel, you will see that it is lower, shallower, but the idea is that the top will be in the center, but because it has quite a lot of data points in this, well, let's call it the 60% area, but the sort of not the center, but slightly away from the center, your normal distribution rules, and again, this is not a good normal distribution, but if you just put the formulas in there, we'll assume that they have to correct for very long tails. Because if you have a wide spread in your center, you also expect that you have a wide tail. What is the actual problem with this? And let me get something like a specification marker here. Let's say that we have a minimum weight specification. Our products should be higher than this minimum weight. If we take the average weight plus the standard deviation, and then we say, for instance, we want 3 standard deviations to be relatively sure, so that's a CPK of 3 at least, relatively, CPK, sorry, of 1, 3 standard deviations, that we are above the limit, then we have to move this whole thing, because the 3 sigmas, they say, well, you have quite a way to go. But when we do a really good analysis on the underlying data, so if we can split the streams of the packages, the products coming out, we see that actually the chance of hitting a very low value is a lot less. So basically, this process, even with the double dosage system, would fit nicely above our weight limit. But when you get the statistical standard deviation and just assume normality, you are going to push this further out. Now that costs money. If we're going to move this to a higher weight is more material, is more money, is a loss for your organizations. It's even sort of Coming back to a previous video where we had a bit of a discussion with Paul Allen about do you need to know the underlying stuff and the histograms. This is one of the reasons why you need to know about at least the concepts of normality. I will say this can also be solved with a histogram, because if you have a histogram of a lot of data, and for this you don't need advanced statistics, right? You will see that you get sort of a block here in the middle with basically nothing to the side. So you will see that you get a much broader top-heavy bell shape than you would expect in a normal distribution. If you then plot this one over it, you will see that it goes sort of under the distribution columns that you see and off to the sides, and then you already have a very good clue that it is not the proper way. You will see the same if you make, and in that video I used the other way around QQ graph. Let me draw a new Q graph to test for normality. You would expect your values to be on the normal distribution line, so the values have to be in this diagonal line. But what will you see when you test this system? So in fact, this line assumes the red standard deviation, right? The normal distribution that you calculate based on all the rules. So those, they try to catch the same thing. Now let me get my green marker as well. And what you will measure when doing this is off to the sides, you have much fewer hits than you would have expected. So the dots go like this. See, there's too few on the top and bottom and too many in the middle. And if you have it extreme enough, it will also give you this is no longer a normal distribution result from a QQ analysis. But this here is something that actually it happens quite a lot. And because it happens quite a lot, we also have a number of ways to check for it and to deal with it. And that's why I just wanted to get those together, right? Because at this moment I sort of already know where the problem is, and I also gave that thingy away in the beginning of the video. I have a double dosing system, but you also want to check if this difference is there. What you see in a SPC chart, a statistical process control chart or a run chart, is that we can check for this rule of stratification. And stratification is that it goes up and down and up and down and up and down and up and down. And then the sort of the standard rules have either 14 or 15 consecutive above the line, below the average, above the average, below the average. And then it gives you an alarm that says, well, you're probably looking at 2 data sets. And of course, one of the better ways is to actually go to the process. And if you know that this is happening, just manually sort them out to at least prove your theory. And then all kinds of t-tests, but especially here the 2-sample t-test to check. We have a sample of all of our left nozzles, we have a sample of all of our right nozzles, and we take the average per nozzle, get also those standard deviations, compare it, do this 2-sample t-test, and check if those 2 samples are statistically just one big distribution. That is, the difference is neglectable compared to their own spreads. So if they have a very wide spread and the difference is relatively minor, your t-test will say just treat it as one population for purposes of statistics and normality. But if your t-test will say there is a significant difference, what that means is that the distance, so the structural error between those 2 nozzles is so high that it will really influence how you do the rest of the statistics. It will really have an effect on how you look at your system. So those are a bit the things you can do in practice. Now, as soon as you know what is happening, you also have to adjust your measuring equipment, or at least your data analysis, and you're going to have to get something in place. Now, the best, of course, let's start with that. The best is to eliminate this difference, right? That is what is going to be your first goal, is to just make sure that the left and the right nozzle, or in more complex equipment, all 6 or so nozzles, are giving the same volume, the same weight, or the same temperature, whatever the same. And this way you really solve the problem for your factory and for your customer as well, because they are also counting on you to get a stable product. So that is why split them up, test it, do some resetting, do some retooling, test it again, see if you can get those together. Now, this physical fixing of the problem might not be as quick as you would like it. So what do you do in the meantime? Are we going to move the whole average upwards and just be spending more money on the product? Or can we also get around it for a temporary solution? And I think that just looking at the economics of it, it might be worth really calculating how much do I need to be away from my limit by getting the standard deviations of these individual sites, so these individual nozzles, individual populations, and also the difference in their respective means. And with that, you can have half of the difference of that mean plus 3 times the standard deviation of one nozzle to be your overfilling, your distance from where your limit really has to be. Now, again said, this is, I think, a temporary fix. In the end, this just buys you time to make sure that your process is set up correctly, because we want to be creating a uniform product and really driving up our CPKs and reducing the spread in our process. That is what Six Sigma is all about. But in the meantime, maybe this will buy you a little bit of time and definitely buy you some savings or some peace of heart during which you can really solve the process. On the solving part, we again go back to our friends, the t-test and also the difference of means. And there what you just need is you need a lot of samples of both sides of the nozzles so that you can actually make these distributions. So go for 50 samples at least of either side. I mean, we are doing, again, standard deviation normality type of calculations. 30 is the bare minimum, but better is 50 or a bit more. More than 100, not really needed. So unless you have really nice automatic data collection, why go for it? But if you do measure it manually, yep, you're in for 50 products, please, at least, per nozzle in this case. So then you have the means, and then recalculate it, right? And here we get into, and I like this idea, a Six Sigma student should not study statistics as much as they should be studying physics, because you need to adjust your equipment on this. So if you have, and what I have in this example for me, but translate it to your own, a couple of cylinders doing the filling, and a plunger going up and down, then when we see that this cylinder is a little bit wider, or for some reason gives just a little bit more, we check this difference and we calculate. So how many grams do we need to take away? And just fill up the grams here. So for instance, make this a bit thicker, so that you, in the end, can compensate and get those cylinders to be physically of the same size. Maybe you can get smaller ones. Maybe it is something here in how they are pumped and driven, because of course these will have a driving mechanism that really pulls them down and up. A slight adjustment on the position of the pin on this wheel, or a slight adjustment on a servo motor can have the same effect. But use this, so we calculate the averages. We know that it is so many grams or pounds or liquid pounds or whatever, but let's keep our engineering in the metric units. So many grams. And what does it do with our physical system? Do we need to reduce the cylinder size, do something with how it is pumped, Is it perhaps the servo that is a bit too slow opening a valve? Because that is also very possible. The valves that are on top that open or close the product flow, maybe one of them, the spring is not good. So these are the typical things to check. Oh, and again, here also I notice I jump into fixing stuff. That's because I'm already checking, but the first things you need to do whenever you encounter this is to restore the basic conditions. And the basic conditions here are definitely also checking, do I have the same bolts in here? Are the valves still working? Are any vacuum or pressure air hoses blocked, or is there perhaps a spring that is not good anymore? So all those things with reaction times, all the sort of the usual suspects in bad movement, is it maybe not lubricated enough, things like that. That's of course the first thing to check. Now, for mine it wasn't really that simple, but we'll get into it further and see if we can really work them and put them together. Just for now, I was forced to go to this system and at least see a little bit how close can we be to the minimum line and not go over any legal boundaries before we start really modifying something here, replacing one of or both of the cylinders so that they are really the same, and we can get rid of, which is for our product, a couple of percentages of difference in weight, and that is quite a lot. Bit more of a rant than usual. I hope you forgive me the lack of structure, but that is also because I'm trying to put in a use case that actually I am still working on, so I also don't know the final answer yet. I just know what first steps we did and what the rules and the experience of Six Sigma tell me. Where do you go? How do you really attack it? But I wanted to share this with you because it's not the first time I've encountered this. In fact, I've been tackling this type of problem quite often. And I thought it would be nice to also share it with you, really be on the lookout for a hidden double or triple or more, but a double distribution within your normal distribution. And the first sign you will get is you get a very high standard deviation, much higher than you would actually expect, especially also higher than when you're just at the line and weighing some products or looking at the parameters and they seem to be okay, but the machine tells you that there is a huge spread. There is a good chance that it is factoring in a secondary, but also normally distributed process. The same type of process will also happen when you are slicing a big product in nice and equal slices, so very nice, strict, normal distribution, and then the end cap is registered also as a slice. It's not completely correct, but most machines don't really sort it out. So they will also weigh that end cap, throw it away, but then you get a secondary, much higher, or sometimes much lower distribution. And what can even happen is that you get both of them, right? High and low, and then you just get a broad distribution, although actually the underlying physics tell you to ignore, remove these data points. So looking at your process, seeing what the physics are doing, so what the real parameters of your process are, and if you see such things happening, like my two nozzles giving both quite a stable but a separated weight of the product, or you see that a first or last slice is always a bit different, but it's still weighed, and then a weighing machine, a check weigher, throws it off the normal line, but you still have this data point, know that you have to ignore this data point. So the physics move over into the statistics. I always tell at least black belts, master black belts, they should definitely know what the statistics are doing, also to know which data to disregard. Because if you are just disregarding the top and bottom based on such a graph, you run a very big risk of simply not having a normally distributed system and data collection and making your data fit the statistics, which is a mistake, because then you are doing your calculations, very nice, but they are not reflecting your physical process, big risk. But if you know that physically your process needs a logarithm to better indicate, or to disregard the last weight in every series of weights, or to look for odd and even products, right? So every odd product is a separate distribution from every even product. Things like that. If you know this, then you can improve the statistics and the calculations afterwards. So anyway, hope that it shook some ideas, that it got you some inspiration and maybe a new way to look at your processes. I wish you the best of luck with improving those processes. And as always, don't forget to enjoy the improvement journey.